Thank you for joining us for the complete guide to sizing injection molding machines. This is part 4, why the materials matter. So when you're speccing out your molding machines, you first want to know your materials. Outfitting your plasticizer for the proper material can lead up to a 25% cycle improvement and part rejections of less than 0.5%. And specifying the proper plasticizer for your material may lead to a much longer life cycle of your screw and barrel. So take the time. It's worth it to generate a proper specification for your machine. So let's look at some of the major factors. The degree of crystallinity. This is the resistance to deformation as heat is applied over time. And there are two different types of crystallinity, amorphous and semi-crystalline. So let's look at some amorphous materials. An amorphous softens gradually with no defined melting point. These are materials like polystyrene, ABS, polycarbonate, PVC. They are slow to absorb heat. They're shear sensitive. They require longer transition zones on your screw with deeper channels for lower compression ratios. Whereas semi-crystalline materials, they remain a semi-solid with a quick transition melting point. And they're materials like polypropylene, polyethylene, nylon, PBT. These are less shear sensitive materials that require shorter transition zones on your screw with shallower channels for more shear in your material. A compression ratio is the difference between your flight depth and your metering depth. So as we look at a couple of different compression ratios, let's focus on a GP screw. A GP screw traditionally is going to have a 2.5 to 1 compression ratio, and this is generated by dividing the feeding zone by the metering zone. That's where you come up with your 2.5 to 1. Compared to an amorphous material, which would have a compression ratio more along the lines of a 2 to 1, whereas a semi-crystalline material would have a compression ratio of 3 to 1. So let's look at viscosity of your material. Viscosity is the resistance of the melt to flow under pressure. And this is generally measured in what's known as a melt flow index described in ASTM standards, where you have a given weight pressing on a cylinder that is pressurized to a given temperature with an output of weight over a 10-minute period, and in this case, grams per 10 minutes. So a high MFI material is going to be a low melt viscosity with lower resistance to flow, requiring shallower flight channel depths to use more shear on the material, versus a low MFI, which is a higher melt viscosity with higher resistance to flow, which would generally require deeper flights with less shear. And how about additives to your materials? Some affect only the screw geometry, while others will also affect the screw material and barrel materials. Additives are generally heat sensitive, shear sensitive, corrosive, or abrasive. Typical additives that you will see are color concentrates both in pellet and liquid form, organic fillers like glass and mica, UV stabilizers, blowing agents, and slip agents. And in almost all cases, these additives are going to increase the viscosity of your melt, generally requiring deeper channel depths on your screw with lower compression ratios. And this is most important for glass-filled fibers to prevent premature breakage and premature flight wear, to have the deeper channels. Let's look at the material density and the output factors of your material. Almost all material suppliers will be able to supply you with 1, the solid density of your material, 2, the melt density, and 3, the bulk density. And all 3 of these densities are important for calculating your residence time on your barrel. But there's one more density that must be considered. Almost all OEM machine suppliers, when they quote you machine specs, are going to be talking about an output factor. And what an output factor does is take into consideration the non-return valve and its behavior on the amount of material that the machine has an output for volumetrically. So if we look at polystyrene, which is what most machine manufacturers are talking about, you'll see it has a melt density of 0.97, whereas the output density is 0.91. This has to do with the amount of material needed to set the check ring. And the same thing is true for polyethylene. Polyethylene has a melt density of 0.73 with an output of 0.71. Again, that has to do with the non-return valve. But how about when you have fillers in your material? You can see down below for polypropylene, when you add 20% talc, it takes your density up to 0.85 versus glass fill, where you can see with a 40% glass fill, you've got a 0.98 gram per cubic centimeter density. So fillers always increase the average density and increase the shot capacity of your molding machine. So take that into consideration when speccing out your machine. Let's talk about residence time. This is the amount of time the resin is in the barrel before it's injected. The most common mistake that molders will make is just dividing the shot weight by the machine capacity. Let's look at a general purpose screw with a general feed, compression, and metering zone, assuming you've got 100% shot size, and we use 30% of it. 30% would tell you that you've got 3.3 shots capacity of residence time. But what about all of that material in the barrel? That calculation is wrong. We need to be considering what's on the screw inventory as well as the L over D. There is a lot more material on that screw, both bulk density, bulk and melt density, and then the melt density going through the metering zone. And that also doesn't take into consideration what L over D screw we're talking about. As you can see here on the screen, we have an 18:1 L over D, and down below we have a 24:1 L over D, both with the same shot sizes. So if you were running a 24:1 L over D, you'd have a lot more material compared to your shot size. So true residence time incorporates the feed zone inventory in bulk density, the transition zone inventory in both bulk density and melt density, the metering zone in melt density, and the shot volume in melt density. Having a mistake in this area could equate to a 20 to 40% difference in your residence time calculation, which could be a big problem on some of the materials you might be running. So let's look at some of the key takeaways from this video. Take the time to evaluate your materials with your machine supplier. The crystallinity and the viscosity determine the screw geometry and the compression ratio of your screw. Additives may require different screw geometry, coatings, and armoring of your screw and barrel. The output density is different from the solid density, the melt density, and the bulk density. And know what your residence time truly is. In our up and coming videos, we're going to touch a little bit more on screw geometry, fast cycle machines, auxiliary machine functions, and automation. We hope you've enjoyed this video. If you'd like to contact us, please do so on the number on the screen, and you're welcome to contact me directly on my email as well. We hope to have you next time, and thank you for joining us.